And next, it's my pleasure to introduce to you Professor Rosanna K. Olsen. She is a senior scientist at the Rotman Research Institute and an associate professor at the University of Toronto. And she will talk today about scene-sensitive medial temporal lobe subregions being recruited for the integration of non-scene stimuli.
Hi, it's my pleasure to be here today, and I look forward to building on some of that beautiful work that you just saw from Marshall and understanding the organization of the medial temporal lobe. I have no disclosures. So for those of you who study memory, what I'm about to say is no surprise. The hippocampus and the surrounding medial temporal lobe are critical for episodic memory, but yet a lot is unknown still about the way in which these memory representations are organized in the medial temporal lobe itself. So first I'd like to introduce you to this idea of memory binding. So you just watched this talk by Marshall. It took place in Brisbane, and he talked about his tractography work in the medial temporal lobe. My display went away, but I don't need it. It's okay. Yeah, it's okay. And you might form a memory formation, you might form a memory between these two elements, Marshall and Brisbane, and also the content of his talk, and that, again, we call that binding. And then the next time you see Marshall, you might remember, oh, I saw him give a wonderful talk in Brisbane. And so you might have a cue, which is Marshall, and then a process called pattern completion occurs in which you remember an associated place in which you saw Marshall before. But again, the neural substrates of these processes require further study. Now, Marshall also introduced you to some of the organization of the medial temporal lobe. You saw that entorhinal cortex has projections into the hippocampus, and we think that this circuit is very important for different memory processes. I'm going to refer to this as organization that goes from the entorhinal cortex through the subfields as the transverse organization. But we also know that there's another organization, which you also saw in some of Marshall's slides, which is the long axis organization, where there's different connections between input structures and it looks like different output structures from the hippocampus to different portions of the brain, depending on whether you're the anterior hippocampus versus the posterior hippocampus. And so we think that both of these organization schemes are important for understanding episodic memory. Of course, both of these axes are probably important, not just one or the other, so transverse as well as long axis. Now, the theories that have focused more on those transverse axis organizations have ascribed particular roles to subregions like CA3, dentate gyrus, and CA1, and you're going to hear a little bit more about that from Helena in her talk, so I'll let her cover that. And then when you look at the long axis organization, we see specialization, again, depending on where you are in the medial temporal lobe, anterior versus posterior. And some theories have emphasized this role and have talked about how areas of the anterior hippocampus versus the posterior hippocampus and areas of anterior MTL versus posterior MTL are sensitive to different types of stimuli. So, for example, many studies have shown that scenes are very strongly activate the parahippocampal cortex, and faces more strongly activate the perirhinal cortex. And in this study, where we grouped across many different studies, this is a sort of a meta-analysis, we also saw entorhinal cortex showing more preference for faces as well. Now, when you look at the hippocampus itself, the picture gets a little bit less clear in terms of the anterior to posterior distinction. So that might give you a little bit of a hint already that there might be something going on in terms of the hippocampus where it's not necessarily as tied to the stimulus content itself. Now, in addition to stimulus content, there's other theories that have been proposed about the long axis of the hippocampus. For example, some studies have focused more on processing requirements, such as novelty encoding or integration in the anterior hippocampus, and other studies have pointed to the role of the posterior hippocampus in differentiation and also spatial navigation. So lots of differences between the anterior and posterior hippocampus. Sorry, and the anterior and posterior medial temporal lobe in general. So I already introduced binding, but now I'm going to introduce another memory term called integration. So this time, let's say you saw Marshall's talk in Brisbane, and then tomorrow you go to Lucina Uden's keynote lecture. And even if you never encounter Marshall and Lucina Uden in the same room together, your brain is going to form an association, or could form an association between Marshall and Lucina Uden indirectly, because you experience them within the same context. And so this is called integration or associative inference. And many paradigms have been developed to study these types of inferences, and that's the type of paradigm that I'll describe to you now. And different regions within the medial temporal lobe, including the hippocampus, of course, have been linked to associative inference performance. So for review, you can see a paper by Duncan and Schlichting. So in the experimental setting, outside of Brisbane and Marshall and Lucina, we designed a task to study different types of associative inference, where you form associations between objects and other either face or scene stimuli. So on some trials, participants are studying objects with scenes, and then that same scene again with another set of objects. So they study A, B, B, C, and they never see A and C together, but they form an implicit association between A and C, and they can infer that A and C go together. And we explicitly tell people that we're going to test their memory for these types of associations. Now, what we did in our 2019 study was we tested to see whether associative inferences made with scenes differed in terms of behavioral performance between associative inferences that were formed with faces. So another set of stimuli were used, but this time the B item was a face instead of a scene. And in this particular study, we actually saw an advantage for associations that were mediated by scenes. So then we wanted to do an imaging study to follow this up to see if different regions of the medial temporal lobe that are sensitive to faces and scenes are performing content-specific associative inference. So for our research questions, we were interested if associative inference was involved in distinct regions of the brain or common regions of the brain. So for example, previous studies by Meg Schlichting have shown a role for anterior hippocampus and CA1 for doing associative inference, and we were curious if those same regions would be recruited for both associations mediated by scenes and associations mediated by faces. Alternatively, we thought we might see sensitivity within the medial temporal lobe, where regions that are more sensitive to faces might form the associations for those the associative inferences involving faces, and likewise, we might see areas of the medial temporal lobe that are more sensitive to scenes to be the ones that are forming the associations indirectly between the A and C items through the scenes. So again, in our task, just to make it crystal clear, they saw participants in the scanner study these pairs of items, A items and B items. Sometimes the object was paired with a face, sometimes the object was paired with a scene. Later, they would see the face again with a new object, a C object, and likewise, they would see the scene again with a new object, the C object. And they were told to encode the associations between those items, so we actually asked them how likely would it be that you would see that face with the bowling pin, for example. So they were explicitly told to sort of deeply process the stimuli. Now, during the test phase, there's two types of trials. One is just a regular direct memory test, similar to any other associative memory test where you're asking somebody if they remember the association between two things. So in this case, they should say that the basketball went with this person. And then, of course, we also tested the indirect or the associative inference trials, the AC pairs. So in this case, they never saw the spoon with the chair, but they saw the spoon with the playground, and they saw the chair with the playground, so they should answer the spoon. So no surprise that the indirect test is much more difficult than the direct test. So we test for AB pairs, BC pairs, and AC pairs, and of course they're worse for AC. Interestingly, in this particular study, we didn't see that same advantage for the associative inferences that were formed with scene trials. So it was numerically higher than the face trials, but no significant difference there. Oops, sorry. And we conducted high-resolution functional neuroimaging of the medial temporal lobe, where we collected 1.7 millimeter isotropic voxels. We scanned 31 young adults on a 3T scanner. And before they did the associative inference task, they performed a run where they just simply performed a one-back task with scenes, objects, and faces. And when we did a contrast between the faces and the scene trials and the functional localizer, we saw very strong activity, of course, in the parahippocampal cortex. We also saw preferential activity in both the anterolateral and posteromedial entorhinal cortex. And even CA2-3DG, this ROI, showed a preference for scenes and the anterior hippocampal head. Interestingly, none of the regions within the medial temporal lobe showed preference for faces, although the fusiform face area, of course, we checked that to make sure nothing seriously wrong was going on with their analysis, and that did respond more to faces than scenes. But within the medial temporal lobe itself, we really saw this strong preference for the scenes over the faces. So we wanted to look at, so I just told you which regions those are, sorry. We wanted to now look within those regions during the associative inference task. Do those regions show specific activity patterns that are for scene associations versus face associations, or do we see sort of a domain general response in these regions? So the way we addressed that question is we looked during the encoding phase for BC trials. We wanted to see if there was greater activity during BC trials that might reflect the formation of that associative inference or the recall of the A item when they see the BC pair. So we looked within these regions to see if there was higher activity comparing the face trials and the scene trials. And what we found was pretty surprising. So we saw that in scene-sensitive regions, including those two regions of the entorhinal cortex and the parahippocampal cortex, we only saw greater activity in BC trials for the face trials, not the scene trials. So while there was a main effect of activity for scene trials compared to face trials, when BC trials were shown, the only trials in which BC activity was greater than AB activity was for faces. Now turning to what happened at retrieval, so when this is when participants are trying to remember the AC pair, we saw that even though no scenes are shown on the screen at this time, they're only seeing the three objects and they're trying to remember the association. On the ones where they previously saw a scene, we saw greater activity in these scene-sensitive regions, specifically on trials in which they encoded a scene with those objects, which does seem to indicate that there's something carrying over into that retrieval phase as they're trying to remember the scene that connects the two objects. However, the only area that we saw that showed greater correct versus incorrect activity was in the anterior hippocampal head. And the other regions in the entorhinal cortex didn't show that effect. So to sum up, during the encoding phase, we saw that entorhinal and parahippocampal cortex demonstrated increased activity during the BC pairs, but only on those trials that linked the AC items through faces, not on the scene trials, which was surprising. And then at retrieval, we saw that anterior hippocampus showed evidence for associative inference across both types. And again, those scene-sensitive regions did show increased activity when they were recalling objects that were previously studied with scenes. So category-specific activity in the medial temporal lobe was associated with associative inference, but in an unexpected way, where face trials showed greater BC activity in these scene-sensitive MTL areas. We attribute this to the fact that we think that the scene trials already require integration demands that sort of max out the activity in these scene-sensitive regions. And then when you're forming an association with a face trial, the areas of the brain that are involved in integration for scenes come online. We were also surprised that we observed these effects only in the MTL cortex and not in the hippocampus itself, at least during encoding. But again, that sort of speaks to the fact that there's maybe not a pure dichotomy between the hippocampus and the entorhinal cortex in terms of the type of binding activities that those regions can do. And again, we did see this evidence of domain general associative inference in the hippocampal head at retrieval. Just like to also thank the people that did this work. This project actually started right as COVID was shutting down, and so we're happy to see it published, and I'd like to thank my team.